Hello, everyone. Welcome back. Um, Now let's start talk about the coefficient of variation. Section 3.2, part 4. A statistic that allows you to compare standard deviations when the units are different is called the coefficient of variation. And we usually use CV to denote that. And it is actually pretty straightforward. It's just calculated by taking the standard deviation divided by the mean, and then we want to rewrite it in a percentage format. Like for the sample, we have CV equals the sample standard deviation divided by the sample mean, and then times 100% means we write it in a percentage format. For example, we got a 0.79, then that's 79%. And for population, we just want to use the population standard deviation divided by the population mean. They're pretty much similar concept-wise. And then example, I want to compare the variation of the two basketball teams given last slide. So let's just pull out some information from last slide. So for team one, we have the standard deviation equals 2.449. And then the sample mean, we have to calculate that. So let's write down information for team one. We still cannot see that. So 72, 73, 76, 76, 78. So X bar for team one equals sum of X divided by N, which is the sum of all these values. So we have 72 plus 73 plus 76 plus 76 plus 78, which is 375, divided by, we have 5 numbers in total, so that's going to be 75. 75. So that's the mean for team 1. Then we can write it x1 bar for team 1 equals 75, and then standard deviation for that is 2.449, and then x2 bar equals, that's for team 2, x2 bar equals still the same thing, 75, and then s2 equals 6.45. Then CV for the first team gonna be standard deviation for the first team divided by the sample mean for the first team. So that's gonna be 2.449 divided by 75. Which is 3.27%. And then for the second team, the coefficient of variation equals S2 divided by X2 bar, which is 6.245 divided by 75. Which is 8.33%. So now this is larger than the first one. That tells us the first team has smaller variation, or it's more stable. And let's go back to the picture. So we don't see much difference on their height, but for team 2, you do see a larger variation. We should review these two numbers for the coefficient of variation. Okay, now let's look at part 5, Chebyshev's inequality. Chebyshev theorem, the proportion of values from a data set that will fall within k standard deviations of the mean will be at least 1 minus 1 over k squared, where k is a number greater than 1. And then note that k is not necessarily an integer. This theorem states that at least 75% of the data value will fall within 2 standard deviations of the mean of the data set. Why we can say that? Because based on this theorem, when k equals 2, that means fall within 2 standard deviations of the mean when k equals 2. Then we have at least 1 minus 1 over 2 squared. So 1 minus 1 over 2 squared, that's actually 0.75, so 75%. So we can say at least 75% of the data will fall within 2 standard deviation of the mean of the data set. Then furthermore, the theorem states that at least 89.89% of the data will fall within 3 standard deviations of the mean of the data set. Why? When k equals 3, so 1 minus 1 over 3 squared, that's 8 over 9, that's 88.89%. And then now let's look at a real example to verify the theorem, or why we say that at least that percentage of data set data values will fall within k standard deviations. So the real example gonna be for this data set below, we're gonna check how many values, and we're gonna just look at the percentage of the values will fall within 3 standard deviation of the mean. So for this data set, we can calculate the sample mean, which is 6.85, and the sample standard deviation is 3.7387. Just use the formula we learned, we can definitely calculate those two numbers. And the upper limit of 3 standard deviation of the mean. So that means from the mean, so we can calculate a sample mean or sample average. We're gonna look at to the right 3 standard deviations more. What's that value? So 3 times the standard deviations. 3 times the standard deviations. So that makes it a value more than 9. And then plus the mean, so we have 18.0733. So if we draw a picture, look at the distribution. So if this is the distribution of the data set, and mean is right here, then this value is actually 3 standard deviation of the mean. And then the distance is 3 standard deviations. And then we can find another value, which is x bar minus 3s. That makes to the left, you have 3 standard deviations distance. And this range is actually 3 standard deviations of the mean. So this whole range is gonna covers how many data values is exactly what we want to find out. And then now for this example, we can also calculate the lower limit. The lower limit is 6.8571 minus 3 times 3.7387, which is negative 4.3590. So from this value to this value, that is actually 3 standard deviations of the mean. So left or right. And then we just count. This is a range. And then we look at our data set, how many numbers are within the range. So we can check all of our 14 values are within the range. So so 14 values within the range, compare with how many numbers we have in total, that's 100%. So we have 100% within 3 standard deviation of the mean based on this data set. And from the theorem, we can know that at least for any distribution or any data, we have at least 88.89% of the data values fall within 3 standard deviation of the mean. So the real thing is 100%, and then based on the theorem, we can say at least 88.89%. So which is correct, but not as precise. So one thing again to mention here is Chebyshev inequality applies to any distribution regardless of its shape. So we can have left skewed, right skewed, or symmetric distribution. Okay. And then let's look at part 6. The empirical, or we call it the normal rule. For more precise approximation, when a distribution is bell-shaped, or what is called normal, so we'll define this term later when we talk about the continuous distribution. So the following statements which make up the empirical rule are true. So we have 3 statements for the empirical or normal rule. We're going to say approximately or about 68% of the data value will fall within 1 standard deviation of the mean. So now we never say at least, we say it is about this much, so it's more accurate. And then we're going to say 95% of the data value will fall within 2 standard deviations of the mean. And about 99.7% of data value will fall within 3 standard deviations of the mean. And again, this is not for any distribution. So this is only for when the distribution is bell-shaped. So again, bell-shaped is something like this. This is bell-shaped and symmetric. So if in a picture, we can still see the 3 statements. So if this is our sample mean, then 1 standard deviation to the left. So this distance is now 1 standard deviation, and then this is 1 standard deviation. So 1 standard deviation away from the mean. So this range covers 68%. And then this is another 1 standard deviation of distance, which extend to 2 standard deviations away. So this whole range covers 95% approximately. And it withstand another standard deviation away. So from here to here, that's about 3 standard deviations away from the mean, x bar. Then this covers 99.7%. And we can actually make it more accurate. So because normal distribution is a symmetric distribution, if we say from here to here, that's 68%, then what about half? So from here to here, so this is actually half of 68, which is 34%. And what about this? So 2 standard deviation weight, we know is 95%. So if we say this area is 68%, then the area, which includes these 2, but this 68%, which give us 95 minus 68, that's 27%. 27% because it's symmetric. So this area equals the left one equals the right one. So 27 divided by 2, which is 13.5% for this area. And then same thing for this one, we still have a more specific information for that. Let's calculate that. So 99.7 minus in the center 95%, which is 4.7%. So 4.7 divided by 2, so 2.35% for each of this area. So we're not done yet, right? For all the area under the curve, we still have this little areas here, and then this little areas here. So 99.7, everything under curve is 100%. So for this one, gonna be 100 minus 99.7, which is 0.3 divided by 2, so 0.15%. 0.15%. So we have make this empirical rule more specific. Now let's look at practice 1. So adult IQ scores have a bell-shaped distribution. So when we look at bell-shaped distribution, we know we can use this empirical rule with a mean of 100 and a standard deviation of 15. So what percentage of adults have IQ scores between 55 and 145? So now we know the mean already. We know the standard deviation already, and we know the to limit 55 and 145. So we can actually calculate 155 compared with the mean. The distance is how many standard deviations. So 145 minus 100, that's the distance. And then we can just think one standard deviation is a value of 15, and then this distance is how many standard deviations. How to calculate that? Just divided by the value distance, the value standard deviation. So we have a distance of 45 divided by 15. That is 3 standard deviations away. And then same thing for 55. That's also 3 standard deviations away. So this is 3 standard deviations to the right. And this is 3 standard deviations to the left. To the left. And now this question is actually asking for a bell-shaped distribution or normal distribution. What percentage of data will be between 3 standard deviation away from the mean? Then based on the empirical rule, so approximately 99.7. So we just answer 99.7%. And practice 2. And adult IQ score is still the same setup, have a bell-shaped distribution with a mean 100 and standard deviation of 15. What percentage of adults have IQ score between 55 and 130? So same thing, we look at 130, compare with the mean. So minus the mean 100, and then divided by the standard deviation. So that's going to be 30 divided by 15, which is positive 2. So that means 2 standard deviation to the right. So positive mean to the right. And we use 55. Look at the minus 100 divided by 15. So we got a negative 45. So 55 minus 100, that's negative 45. Negative means to the left. So the direction is to the left. And then you have a 45 distance divided by 15, that's negative 3. So that means 3 standard deviation at the distance to the left. Now, this question is changed to for a bell-shaped distribution, what is the percentage that the data follow between 2 standard deviation to the right, between 3 standard deviation to the left and 2 standard deviation to the right. So we can look at our specific distribution plot. So we have 3 standard deviation to the left. So that's from here, 3 standard deviation to the left. Let me use another color. So 3 standard deviation to the left, and then 2 standard deviation to the right. So these whole area. So we have 2.35%, 13.5, 34, 34, and then 13.5. So we're just gonna add up everything together. So actually this 4 add up together equals 95% and then plus 2.35%. So this is gonna be 95% plus 2.35%, which is 97.35%. So this is the percentage. Okay, so that's all for section 3.2. Thank you.